ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో NBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Last class we have discussed introduction, radiation mechanism, a single wire and two wire dipoles. Right now we are discussing a current distribution and a thin wire antenna and some of the radiation parameters. Okay, right. Again, just look back once. Just whenever we are analyzing, we are studying the concepts of antenna, all of you please keep in mind the basic structure of the antenna, the basic picture what we have studied earlier. So it is a one source like this. Suppose all of you please assume an off wave dipole antenna. Okay, so this is one voltage source. This some source is attached with some a off wave dipole structure. This is a positive dipole and this is a positive pole and this is a negative pole. So if you assume it is a transmitter, the same thing at the receiving end also. So this is what sorry. So it is a receiver section also. So here the thing is like this. Sorry, this is not one. I will erase. The same dipole structure and the same center fed source again at the receiver. Here we are studying what we want to analysis. Suppose it is a transmitting antenna. If it is a receiving antenna, by exciting the voltage source, it continuously propagating some waves. It is not a number, it is continuously propagating some waves into the free space. So antenna, how can I define some other way of the definition of the antenna? It is a link between the free space and a transmitter, or a link between a free space and a receiver. So antenna is also defined as a link between a free space and a transmitter, or a free space and some receiver. So this is the basic structure of the antenna. From this, the basic picture of the antenna, we want to analysis, we want to study what is the strength of these waves in free space, as well as at the originating points and as well as at the receiving points. So likewise some field strength, like some other parameters which may encounter one by one right now. So this is the main thing when we want to study antenna. All of you please remember this whole picture in your mind whenever we want to study some concepts, some antenna concepts. So some I will tell you something right now. So antenna is a basic component of the systems. So suppose what is a system? A system is a combination of some sort of things. So it is in if you observe, this is one part, that is what we call source, and this thing is a one pole and this is one pole. So the complete, this one is a off wave dipole, and these things are a free space waves, and this is the transmitter section, and this is the receiver section, and this is the transmitter section. These sessions, these things, that means in the source, the off-wave dipole, the free space, all these things are followed by some specific system, some specific rules that leads to a system. A system is nothing but which follows some rules by merging some things. Okay, so all together these things is called an antenna system. The basic components of system, where it is used a link between a transmitter and a free space, or a free space and a receiver. Okay, so different antennas are used in different systems. Suppose here we placed what is this one, some source. Okay, so different antennas may use different sources. So that is I mentioned here, different antennas are used in different systems, in different forms. But irrespective of the type of the system, whether we are using an irrespective of the type of the system, a type of antenna application, all the antennas possess some fundamental properties which are same for all systems. Earlier we seen some types of systems, like pyramidal antenna, or parabolic antenna, or some a loop antenna, like this, some loop antenna. We have seen all these systems. So irrespective of the antenna, irrespective of the type of the antenna, so whatever the antenna you want to study, all the antenna systems possess some basic properties. So those basic properties are radiation pattern. Okay, I am not writing fully here. It is better to study rather than PPT like this one. So a radiation pattern, a radiation intensity, a power gain, antenna efficiency, aperture, radiation resistance, like this. Like these some of the what we call parameters is there, that is which we are going to study right now. So in this one, very important thing, the first one is an isotropic radiator. So before explaining the isotropic radiator, I want just explain the graphical representation of the radiation pattern in antennas. Graphical representation of a radiation pattern in antennas, right? Okay, all of you please look at once, graphical representation of the radiation pattern. Suppose if you I am not writing fully, all of you please assume this is one antenna. This is one antenna which is a some source with some internal circuits. This a rectangular box, what I have drawn here is an antenna. Whenever this antenna is excited, whenever this antenna is excited, so automatically there will be electric field generation. So whenever an electric field is generating, automatically there is a, yeah, as we studied earlier in EMWTL, electromagnetic waves and transmission lines, automatically there is a by using right hand thumb rule, there is a electric field and magnetic field also. So whenever, suppose by using thumb rule, okay, like this, if there is a magnetic field is produced, and in the reverse section there is a uh, electric field also produced. So that is E plane and H plane, E plane and H plane. So Practically, I will explain right now. So all of you please keep in mind, both E plane and H plane, both electric field and magnetic field, both are generated whenever the source is excited. Very important point is. Uh, so again, this antenna I am placing down here. So this is another type of antenna which I place. This is also rectangular shape. I place it here. So whenever the source is excited, the radiation pattern. This is like this. Radiates uniformly, not uniformly. I will explain. This is the uh, graphical representation of an antenna. Practically, an antenna cannot radiate energy with the same strength uniformly in all directions. Okay, radiation is large in one direction. So, this is what we call. Uh, I am drawing here, which you see. Okay, this is the radiation is maximum at this point, minimum at this point. Okay, so the radiation it is found that the radiation is large in one direction while zero or minimum in one direction. Here, if we found here at this point, so it is zero. It is zero. If you find here, it is a maximum radiation here. This is a maximum radiation. So it is found that the radiation is large in one direction while zero or minimum in some other directions. So the radiation from the antenna in any direction is measured in terms of field strength. Is measured in field strength at a point. I will explain how the field strength can be calculated right now. The field strength can be calculated by measuring voltages. Okay, by measuring voltages at 2 points. Suppose if you want to calculate the field strength of here, this point. If you want to calculate the field strength of this point, okay, how can you calculate? How we calculate the field strength of this point? With reference to the basic generating the basic point, the basic source at the exciting point, so here, the basic exciting point here. The volt, suppose let us take this is our reference point, the first one. We want to calculate the field strength of the device here, not a device, it is the field strength of the wave. Okay, with reference to this point, how can you calculate the field strength is, okay, the difference between the two voltages, here is some voltages, here is also some voltages, the difference between these two voltages by the distance between them. So that is a distance I am writing here. So difference between voltages difference. So voltages difference means again you get voltages by difference, that is distance means uh, it is a distance. So finally what we get, volt per distance, that is volt per meter, volt per volt per what is that, volt per meter, right? So volt per meter is the measurement of unit of what we call field strength. Field strength is nothing but, again, in generally, the strength of the field. The strength of the field. In generally, we speak what is the strength, what is the strength of the wave, what is the strength of the wave propagation here, or what is the strength of the wave here, or what is the strength of the wave here, what is the strength of the wave some other point. Suppose if you want to calculate the strength of the wave, the strength of the field there, then the difference between the voltages difference between those two by the distance between them, that is volt per meter. So volt per meter is the one simple measurement of what we call volt per meter is field strength. So the field strength is nothing but volt per meter. Generally, field strength is expressed in millivolts per meter. Millivolts per meter. This is a field strength pattern and a radiation pattern. The radiation pattern of an antenna is one of the important characteristics of antenna, because it indicates what it indicates. Field strength indicates what? So, by observing the field strength characteristics, it indicates distribution of the energy. Distribution of energy radiated by antenna in free space. So, whenever we calculate the strength of the wave here, automatically we can calculate the power radiated also here. So field strength gives some details about the energy radiated by the antenna in free space. So this is one of the important characteristic. What is that one? Radiation pattern and a field strength. So what is the unit of field strength? Millivolts per meter. In general, a radiation pattern is nothing but a graph. In general, a radiation pattern is nothing but a graph which shows the variation of the actual field strength. It shows actual variation of the field strength. So, sorry. Another the definition of the field strength pattern. If the radiation of the antenna is expressed in terms of field, it is called field radiation pattern. At the same time, if the radiation of antenna is expressed is what we call expressed in terms of power per unit solid angle, that is a power radiation pattern or a power pattern, simply a power pattern. So before going to next topic, I want to include something right now, that is an isotropic radiator or isotropic antenna. An isotropic radiator or isotropic antenna. What is an isotropic antenna? In general, suppose with reference to this antenna which I drawn here, suppose if I place some isotropic radiator or isotropic antenna, what is the difference between this isotropic antenna and this normal antenna? So the first point I want to conclude you, generally practically there is no isotropic antenna exist. So first of all, what is an isotropic antenna? The isotropic antenna radiator is a radiator which radiates energy uniformly in all directions. Uniformly in all directions. Actually, I have drawn here like this, right? So at some places it is 0, at some places it is minimum, at some places it is maximum. But what is an isotropic radiator? It uniformly distributes its energy in all directions. Practically there is no antenna at a uniform direction. That is, everywhere, whenever, wherever you may find one point, it radiates uniformly. So it is again, an isotropic radiator is defined as what? Which radiates energy in all directions. Like in all directions, if you find out whether this point or this point or this point or somewhere, at any point the energy radiation is same. So it's quite typical. Suppose in general, if the amount of energy here is not the same as here, definitely when the wave propagates, wave traveling from some point to some point, automatically some losses is there. But an isotropic radiator tells us which it radiates energy in all directions uniformly. So it is an isotropic source. So it is also called an omnidirectional radiator. It is also called a lossless ideal radiator of an antenna. So with reference to this isotropic radiator, we have some equations are there. Okay, power radiation. We want to conclude some equation right now. Okay, all of you, I will I will write two lines of equations right now. All of you, please. Okay, right. Consider an isotropic radiator is placed at the center of the sphere. I am not writing the sphere. Center of the sphere at a radius r. Radius. This is the radius r. All the power radiated by the isotropic radiator passes over the surface of surface area of the sphere given by, so area of the sphere 4 pi r square. I think all of you know it. 4 pi r square. Area of the sphere is 4 pi r. Again, this is one antenna, that is a radiator in which is placed in a sphere at a distance r. The area of the sphere is 4 pi r square. 4 pi r square. So we are mentioning it is an isotropic. Again, clearly, isotropic means there is no loss here. Wherever you find wherever you want to calculate its energy, it is the same. It is uniformly radiating, so that a zero absorption of the power, zero loss of the power. Then at any point of the surface, there is a pointing vector is there, P bar, gives the power radiated per unit area. Power radiated per unit area. Okay. So in ideal condition, we have some radial components is there. Two directions. One is a electric field and magnetic field. There is also two directions, theta and phi directions. In general, normally at the first conditions, P power radiated power P theta equal to P phi equal to 0. P theta equal to P phi equal to 0. So the total radiated power, that is P radiation. The total radiated power is given by a double integral. Why it is a double integral? One is for electric field, one is for theta, one is for phi. So normal power into P bar into ds. So in general, P is nothing but power radiated at PR. Okay, so by PR is a PR is coming back to here. Then again we get integral ds. Surface double integral of ds is nothing but 4 pi r square. So this is a P radiation. So if this PR is nothing but P average, this is a P radiation. Okay, this component is replaced by 4 pi r square. So finally P average is equal to P radiation by 4 pi r square. Nothing but it is a watt, power is in watt, and the surface, this is what we call meter square, watts per meter square. This is one of the isotropic radiator. P average power, average power in isotropic radiator is nothing but P radiated by 4 pi r square. This is one of the important characteristic isotropic radiator. Whenever in future sections, if you want to calculate any parameters, power or some other thing, this is our reference. P average, power radiated average equal to P radiated by 4 pi r square. So this is one of the session. In next class, we will look at into the current distribution of thin wire antenna. We will do some problems, radiation patterns in principal planes, main lobe and side lobes, beam width. By studying parallelly with these what we call parameters, and we can practice some problems also. All of you please follow some textbooks available in the internet, okay, or some materials. You please look at into that one. Antenna and wave propagations by GS and Razu is some good textbook is there. You please follow that one. Thank you.